to our crystal phase identification for minerals and advanced materials webinar. So I see that we have 90 people already here, which is really nice. I welcome you all. Please let us know where you're from. We're recording, not recording. We are coming to you from icy, snowy, very cold Berlin. I had to scratch the screen of my car today twice. Because it was very, very cold. And Max and Lucas are in Berlin too. They're just not in the office, coming from their homes. So look at this: Denmark, Romania, Fiji. Well, like Fiji sounds awfully nice right now. So I would like to introduce my two presenters today. That is our head developer, Lucas Wollmann, who also has a PhD in chemistry. And we have Maxwell Turbin, one of our co-founders, and a PhD in material science. So we are going to talk about search match, the basics, and then we show you how you can do this now online using our tool. And we are 105 people joining us from apparently all over the world. Rio de Janeiro, Brazil. Nice. So over to you, Max.
Great, thanks. If I can get the slides working again. There we go. Okay, so you already went into the brief introduction of what we'll do. So yeah, I will give an overview of sort of sample and data considerations to make, because I think we have, and I hope, lots of newcomers to this application and people who maybe want to learn how to do it. And I think it's really important to start with good sample preparation. And then we'll quickly dive right into the actual tool that we created that we hope will be useful for you guys. So yeah, let's get started. So phase identification from X-ray powder diffraction. So you can obviously probably guess that we're very biased to X-rays, but it really is a fantastic and powerful method to determine the ingredients of your samples. I mean, not specifically at the elemental level, although it is possible to get information on the elemental distribution, but primarily for looking at crystalline phases or possibly disordered, and in some cases even amorphous or nanocrystalline phases in your materials, especially when there's overlapping chemistries or polymorphic formations, and you really need to be able to distinguish which forms are present for the properties and understanding of the behavior of material, and also for regulatory purposes or for decision making on how do we process this sample to get the parts that we want out, or for instance, how do we actually get rid of it? How do we throw it away safely? So this is just an example. Actually, we, for the first time last year, took part in the Reynolds Cup, which is a competition for looking at clay minerals. And so this is an old red sandstone sample, which is a common clay containing variety. And so this is just to give an idea of, you can have samples that have tens or more different materials in them, and they're all overlapping. And so you need to have good high resolution data with good signal to noise to be able to differentiate all those contributions. And it's possible to go a step forward into quantification and to really figure out how much of each of those things is in there. And while we won't be going in too much detail into that application today, that's sort of the next step. But really right now I want to focus on just the identification step. How do you get the list of candidates that you think maybe are comprising your samples? So in that sense, there's sort of three steps that you might take for phase identification and quantifying the contents, which is actually searching for candidates. And typically to do this, you either have a structured database like the crystallography open database or like the ICDD, where you can actually pull patterns from particular known structures that might be related to your sample. There's other methods which involve pattern matching. So it's also possible to develop your own database of experimental patterns and be able to match against those as well. Maybe many of you know that we're also building an open measurements database for that purpose. I also won't be specifically talking about that today, but it's something that's coming online soon and will actually maybe provide more features to our search capabilities. There's validation. So of course you can find matches, especially when there's lots and lots of peaks, but you need to make sure that it's actually chemically sensible. Like, would you expect that candidate to show up for a particular chemistry? Preliminary pattern fitting and making sure that if you need to modify those candidates to fit your pattern, does it actually maintain the structural integrity of that candidate? Does modifications to the lattice parameters make sense with respect to the temperature and thermal expansion of the phase? Or do you get weird changes in occupation that are necessary that don't make any sense? And finally, quantification, which requires calibration. So you need to know the proper normalization constants for quantifying the phases. We typically do that with introduction of an internal standard. There's also external standard methods and sort of more semi-quantitative degree of crystallinity methods. And then you can combine that all into multi-phase refinements. And we also regularly do that as well. So today we're just talking about how to find candidates. And that's what our tool does. So I want to take a step back and also, again, for kind of the newcomers, new practitioners that want to get into doing this more, to make sure that there's enough focus towards sample preparation, which is really important if you want to get the best quality data out of a good instrument and have the most chance of successful analysis. You have to have a good sample preparation. And so crystallite size reduction is often an important component, especially when you're sourcing mineral materials, but it could be also if you're growing more single crystal-like or large grains in your particular synthesis. We are working with powder diffraction here. So if you have grains on this in the order of 100 microns, I mean, you're generally talking about a single crystal now. And so you need to choose how to actually break down these particles into smaller sizes so that they're feasible for powder diffraction to sample all the different orientations simultaneously. So coarse powder would be often greater than 10 micron grain sizes, which is still not really ideal. In some cases, it can be okay. Ideally, you want to be in the maximum of 1 to 5 micron range, and actually quite a bit smaller than that is even more favorable. There's also the idea of sort of selecting out grain sizes. And so in certain applications, people will use sieves to actually select out certain particle size ranges. And that can be useful depending on sort of the distribution of grain sizes or whether certain impurities in your sample show up in a larger grain size and need to be removed. But the important thing to keep in mind is that particle size and crystallite size are not the same thing. And with X-ray diffraction, we see crystallite size, not particle size. So you can have large particles that are, say, 50 microns that are actually comprising many small randomly oriented crystallites. So in that sense, you can do a powder diffraction measurement successfully with that kind of sample. And it's for the same reason that we can also do powder diffraction measurements on solid chunks of material, whether it be plastics or alloys, as long as the subgrains within that solid are small enough crystallites and, as I said, randomly oriented. So that's also something useful to keep in mind. Okay, so size reduction technique. Again, not going super into the details of this, but important to keep in mind, different methods are more appropriate for different types of materials. And this is something that you as the synthetic chemist or the person sourcing the material may need to think about, because we want to size reduce sufficiently and randomize the material into a nice powder, but you also don't want to modify the sample. So you might generate a beautiful powder and it's no longer actually the thing that you want to study. So you need to make sure to avoid that. So there's really gentle methods such as hand grinding at a mortar and pestle that are often totally sufficient. There's macrone milling, which is often used in minerals processing, which is using rollers essentially to very gently shear the crystallites into smaller crystallites without generating amorphous content and without heating up the sample substantially. You get into more aggressive techniques with shaker mills and planetary mills, and these are really more to do with applications in mechanochemistry. So oftentimes the purpose is to actually induce reactions or amorphization. So in our case, we don't want to do that. So you may need to use more energy, kind of intensive milling techniques if you have really hard materials. But you need to be sure that you kind of validate that and also are using appropriate settings on those machines to work with your materials appropriately. Okay. There's also the part where you can get too small, at least, for phase identification purposes. And so when you get to nanoparticle sizes are actually generally not really bad. It actually can be quite good. But if you get much, much smaller than 100 nanometers, then you can really have some significant broadening. So what this does, it reduces your ability to resolve distinct peaks. And since in the search match process, we're actually trying to match the positions and relative intensities of those peaks, it makes you less sensitive. And it also degrades the specificity of the lattice parameters. So you might have different candidates of the same class, and you'll have a tougher time choosing which is the right candidate, or maybe even finding it in the first place. So on the left-hand side here, you see what happens to the diffraction pattern of your material as you go from large micron-sized particles down to ultra small 3 nanoparticles. And relatively, you see like your diffraction pattern essentially flattens out when you get to those very small sizes. So that makes it really hard to decide what is your peak position. And on the right-hand side, if I normalize the intensity of those, you can see the comparison a bit better. And what you can see is that even when I go to about 64 nanometers here, so slightly under 100 nanometers, so now we're in nanoparticle size regime, I've lost the resolution of this little shoulder peak here. But otherwise, the peak positions are maintained fairly well. But then you see going to 30 nanometers, 13 nanometers, the peaks broaden out much more substantially as you change the crystallite size further in this lower size regime. And when you get into that kind of sub 10 nanometer, this is where distinct identification of crystalline phases and reciprocal space becomes very difficult. And so that's also not the target application for the database type methods, although it can work for simple structures. And actually, I think in a few weeks, we'll do a session also on what are the options for materials identification in those cases with nanoparticles and even amorphous materials. Okay, one other topic is sample homogeneity and how representative is your sample. This is sometimes less important than the previous case, but of course, make sure that your subsampling is representative of actually the target volume of material. So if you're doing one measurement that's supposed to represent tens of kilograms of material, well, those tens of kilograms of material better be mixed and homogenized well. Otherwise, you need to make many samplings from that bulk. Of course, that's also possible with high throughput measurement techniques. Then you can do lots of duplicate measurements to see how much you're actually varying within the volume of the material, or to also check the statistics of your results, which can be very useful. And you also want to make sure that you're minimizing small populations of large grains. So if you have minority phases that are more like single crystals, or if you have highly oriented grains, which often happens in powder diffraction when you have needle-like or highly anisotropic grain sizes. So you want to try to avoid that. In our experiments, we randomized the sample by vibrating the powders and shaking them kind of back and forth, and that helps to fluidize the powders a bit. But it's also, in severe cases, important to kind of deal with this a little bit in the sample preparation step as well. There's also instances where mixing comes into play. And as I mentioned, for phase quantification, we often mix internal calibration standards into the material to have an absolute normalization of the phase quantities. There's also cases where you may have highly absorbing materials, which don't interact favorably with your X-rays and thereby affect the observation of certain phases through microabsorption effects. So you may mix very weakly scattering filler materials into your sample to lower the overall absorption cross-section. In either of those cases, also very important to homogenize the mixing agent. So typically you'll add that in before you do your milling procedure. In regards to kind of fillers for absorption, to sort of deal with that, we choose to actually run all of our measurements, even the high resolution ones, at high energy. So then the absorption issues tend to be less of an issue. Of course, you may still be working with some very heavy metal material, and then it might be still something important to consider. And I mentioned briefly, preferred orientation effects. So when you have anisotropic crystallites and they may tend to align in particular ways, this can or cannot be a problem depending on the application. So the good thing is that peak positions are generally maintained still. Although if you have severe cases, certain peaks may not be visible anymore. Can also be that if you don't have good powder statistics on the rings, so whereas your rings start to look like lots of spots, those spots may not sit ideally where the average ring position should be. So that can have an effect on the peak position. And then the other consideration is when you use relative intensities in the search match process to also further specify best candidates within a class, then you have this issue that for preferred orientation, in one sense, where you have alignment of grains, you're only sampling the powder grains along certain directions. So you get systematic modification to the relative intensities. And then in a worst case, typically, you have coarse powders where it's still somewhat random. There's no particular alignment of the orientations, but you may have some populations of very large grains. And this just means that you don't have a good powder. So you're not statistically sampling all orientations over all crystallographic directions. And so then you just get really spotty, noisy data that almost start to look like single crystal diffraction patterns. And then, yeah, you're kind of out of luck when that gets very severe. So that's something that you definitely want to avoid through proper sample preparation. Okay, and data processing also can be very important. So ensuring that you've minimized all aberrations from the instrumental setup to the final data are important to making sure you get accurate peak positions and relative intensities. So good calibration of the detector position is very important. Standardization through the use of good reference standards, so typically from NIST, is also very important. And removing non-sample contributions. So we subtract the experimental backgrounds from your materials to make sure that that's not having any effect on the relative intensities. And in some cases, it may be necessary also to remove diffuse sample contributions from your data in order to specifically work with certain more crystalline components. So that's also something that may need to be considered. Okay, so in the essence of trying to keep this quick, now I would actually go ahead and jump into the tool that we've built. And I would just preface this with, it is a sort of beta version of the tool. We think that it's actually looking quite useful, and we're quite happy with where we're at now. And so we wanted to release it to you guys to play with. Hopefully it can be useful already. And we're also very interested in feedback from the community, as it's something that we're continuing to actively develop now and hopefully bring even more powerful features and more robustness to it. So I will go ahead and share my screen. Hopefully this works. Does it work? People see my screen? Okay, so for those of you who maybe haven't already worked with us, and I think Sebastian will talk a little bit more about this in the end, but you can go to our website and there's a login button and you can create an account from there if you don't already. It's also possible to do measurements with us for free to start to actually test this out. The tool does work with uploading your own data to it, but it is sort of optimized for data collected from our setup. I will let Sebastian give more details on that at the end. So I just want to kind of show you some applications and sort of the workflow for the tool. So if you already have an account, or some of you may already have data collected with us as well, when you log into your account and go to your sample list, if you have data already, you'll see in this column called measurements that there are already data populated there from measurements that have been done. So from this view, I may decide I would like to do search match on one of my samples. And I'm just going to start with a really easy case, just to kind of demonstrate the workflow. So you would go to analysis here and then search match. And it is actually possible to do search match on both the high resolution data and the total scattering data. What I would say is I would always prefer the high resolution data for this particular application because you have better separation of your Bragg reflections, which is primarily what we're searching on. But for big nanoparticles or some other cases where you only have total scattering data, it does also work with that, although your chances of finding the right match may be slightly lower. So I'm going to pick the high resolution data to start. It will automatically take you into the tool and already preload the data set. You can also access this from the start just by clicking search match in the left-hand column here. And then you can also load the data from there. So if I go to load data from sample, select sample, and then I have my demo organization, and I can pick my sample here. There we go. And then nothing should change because it's the same one. If the data are collected with us, it will already preload the wavelength from the measurement and also the composition that you put into the sample when you created it. That's okay. If there are other things in there that were not originally accounted for, that doesn't constrain you into any particular space yet. So you can do sort of the quick and dumb thing, which sometimes is actually the smartest thing because it might save you time. You can do nothing here and just say find peaks. And usually this does pretty good if you have sharp diffraction data. I will show you in a bit how to actually modify the peak selections. And then press search. And it should go pretty quickly. And if you're lucky, the first candidate will hopefully be a nice match to your data. So that's kind of the best case scenario. You need to just get the structure for your sample quickly so that you can move to further a Rietveld refinement or some other analysis. We hope that this can be an easy way for you to do that. So if you are happy with this candidate, you can confirm the phase and build up your list of confirmed structures. And if you want to move on from there, you can go to download. And then you should get a zip file that has the CIF files from the crystallography open database. That's something that I should have already mentioned that. Like right now, this tool is only connected to the crystallography open database. So it very well may be the case in certain instances that the structure that you're looking for is not in that database. Then of course you won't find it. We are actively working on connecting this tool to other databases, and I hope that we will in a short amount of time have more possibilities to search that. So just something for you to know. So I would actually just sort of restart that because I want to show some of the other features that will help you specify things a bit more. So if we go again, I already know this sample is titanium dioxide, and I can make the search go quicker if I don't search all the candidates in the whole database. So you can go to required elements and select titanium and oxygen. And then you can adjust the number of elements. I know it has to be 2. So if I do this, then of course I should only search titanium oxide materials. I can click find peaks again, search, and now you see the search went quite a bit faster and I have far fewer candidates. And again, I get my rutile phase. And actually a nice thing is in this case, if I zoom in, I see, well, there's a peak here. There's some other little impurities. There's a few peaks here. So it might be that I have other things in there. Well, of course I do. So I can accept this phase and then I could look and see what else is in here. So actually, if I look at the space group number, I see I get a lot of different rutile entries. But what's this? I have a different space group, and it unfortunately doesn't say it in here. We have to work on massaging the data entries in the COD because actually a lot of the CIF files don't have material names, and I hope that we can provide that in the near future as well. But it turns out that this is anatase, and actually just from that, it must have had, I think you have to at least have 3 peaks from a phase to get it. So it must have selected some other peaks out. But you can see that it gets them here as well. So in this case, I didn't even need to do anything else. It found both of the major phases. Actually, for this sample, it's like, I believe 98 roughly percent rutile and about 2% anatase. So there's some other impurities in there. I don't know what these ones are. Not sure I can find them at the moment. But so that's a way you can also get lucky and find multiple phases without doing any extra work. One other way that you can filter the search, and I'll go through that one more time, is also by elimination. So instead of saying what the required elements are, I can just say what I know shouldn't be in there. So if maybe this was titanium dioxide naturally sourced with some other minerals in there or something like that, well, I might just say, okay, probably not heavy metals, certainly not noble gases, and maybe beryllium, boron, some other stuff that's probably not in there. So I could say it can't be any of those elements. It could be anything else. So these are all a maybe. And then I could search on all structures, let's say from 1 to, I think, maybe 5 or 6 elements would be reasonable. So I can also do the search in that way if I have less starting information about the chemistry of the sample. Okay, so let me refresh, and then I would actually show some different functionality. You
Max,
can also,
Max, one second. There are a couple questions that are related to the database. So the first question, or I think the most important question, to which database was the tool linked? And to which database was it linked? And then the relationship to ICC, ICDD, COD, and ICSD.
Yep. So as I mentioned, right now it only connects to the crystallography open database, the COD. So this is an open source structure database that has, I think, something like, Lucas, maybe 500,000 structures or something like that, roughly, maybe a bit more than that. So it's only searching from that database currently. We are planning to incorporate ICDD and possibly materials project and maybe some other things as well. But currently only COD is available.
And is there an option to upload your own CIFs unpublished and make your own database?
So we do have that. It is not in the beta version right now. I technically can do that. You will not be able to do that immediately. But we're very happy to know that you would like to be able to do that. And it's something that I think we will have available in the near future.
So then one question was about Portland cement, if the COD has that. I don't know if you guys know, but I'm happy, Pascal, to you send us samples and you can try.
Yeah, I mean, Portland cement has a lot of, kind of like common minerals in it. So I'm sure you can find lime in the COD. I mean, I'm not 100% sure, but sometimes the COD has kind of like glaring omissions that are surprising. But I would imagine that you can probably find a few of the ingredients in COD. But you have to test it out. So send us a sample that you want to work with. Or if you already have some data, I'll show you how you can upload it and test it out directly.
And then the last question I think we can answer now is how the score is calculated.
So I'm going to be blunt and say we don't really understand the score. So I'm not going to, lie to you and give you some kind of explanation. What I will say from a practical perspective is you shouldn't really rely on the scoring too much in the current iteration. Oftentimes you'll find the best candidate at a lower score value. I mean, just, to not be like too facetious or anything, like the score is basically a calculation related to the number of peaks and the relative matching and something to do with the intensities as well. We know how the score works, but in terms of like what numbers it gives and when, that's something that we're working on improving a little bit so that it's a little bit more conceptually useful for you in the process to make use of the scores. But to be honest, the scores probably are not super useful for you to go by at the moment, to be honest.
Brilliant.
Okay, so can we continue?
You continue, and after you've done that section, we can answer the next set of questions.
Okay, so what I want to show now is actually, if you haven't measured data with us yet, you can also play around with data that you already have. So to do that, you go data source from file, and then select file. And actually, I wanted to start with something else here. So this is a measurement I did of sulfur at the NSLS, I think 1. So like maybe 15 years ago or something like that. And it's, I don't remember, to be honest, if it's nanocrystalline sulfur or if it is a total scattering measurement. So it might just be that the resolution is not good, but you could take it as either way. So let's say for all intents and purposes, this is very small nanocrystalline sulfur. Okay. And this is the data set that I measured at a different facility or on my lab source. So now you can change the wavelength because I assume it will not be the same as what we use. And you have to enter a composition. This doesn't constrain what you can do with the elemental search, but it is necessary to proceed. So in this case, I know it's sulfur. So I'm just going to go ahead and say sulfur, 1 element, find peaks. And again, you see like the resolution is really low. So it's only getting these kind of very low angle peaks, and higher up, it's just all diffuse scattering there. So I'm not going to be able to do any searching on that for the moment. I could go ahead and do the search very quick. And there we go. There's orthorhombic molecular sulfur 8. And actually, there's quite a few of those in the database. So in this case, the score, the highest value, does give you the top candidates, but there's really only like 3 things in there. there's also these trigonal phase, which clearly doesn't match very well. And there's also a monoclinic phase, which probably, if I'm speaking of visually, looks better to me than the trigonal phase. So maybe you would think that the score there would be higher, but I suspect that the score is higher for this one because it's matching this peak and getting pretty close to some of the other higher angle peaks. So if that gives you a little bit more kind of thought into the scoring. But yeah, just from a kind of general standpoint. Okay, so just to show that, and then I would kind of jump into a slightly more complicated example just to show you a bit more of what you can do with this in a more complicated case. I don't know, Sebastian, if there's some other question we should answer in the meantime.
There is one question. How can we know the CIF number? I think that's what NO CIF number.
Yeah, so I mean the CIF number, I presume you mean with respect to the COD number of the entry.
Yeah.
You don't need to know that. I mean it actually plots it in the outputs. So well, if I just run this again quickly, I can show you. So you have the source here. So, you know, in principle, when we pull structures from other databases, this would be not COD, it will be something else, and the number format might be different. But this is the reference to the COD entry. So there's the number for the candidate. So if I like my rutile phase again, okay, it's this one. That's something that I didn't show before that's actually really useful. So actually, you can check. I can click this link here, and it will open up the COD information card for that entry. So then you can get further information there if you need. I hope that answers your question.
Yeah. The next question, I think we can skip to the end. What the search works with? Only peak max search or whole profile like FPSM?
Currently, the algorithm that we're using is using a combination of peak positions and relative intensities. So I mean, that's very beneficial in a lot of cases because it gives you a bit more specificity in the search. It can be less favorable in cases where you have a high degree of preferred orientation or a lot of noise in the measurement, and then maybe you're just more interested in sort of searching on peak positions. In many cases, it will still give you a result there if it's present in the COD, but that might be something to consider.
Okay.
Okay.
Can it be used for an XRD data collected from powder samples like in the 2 theta range of 20 to 100 degrees, like powder XRD of BAT?
Barium titanate.
Yeah,
absolutely. So I mean the angle range is agnostic, right? Like you can do whatever you measured between 0 and 180. But you have to set the wavelength to the right source that you used. But yeah, there's no requirement that it has to be over a specific angular range. And maybe, you know, for newcomers in the call, I think that's something that's important for people to be aware of, that if you measure diffraction data on different sources with different wavelengths, then the relevant angular range that you'll be looking at can be substantially different. So this still happens a lot for new users with us where, you know, they get these diffraction patterns over like 0 to 14 or 15 degrees. And they say, well, the material that I'm working with has interesting diffraction peaks like around, you know, 30 to 50 degrees. It's like, yeah, but that's on a copper source. And so when you use really high energies, it's contracting your reciprocal space down into smaller angles. So that's why we get a large Q range, which is directly related to the size of reciprocal space that you're probing in a smaller angular range. So that's also something important to know, and also why it's important if you upload your own data, you should make sure you use the correct wavelength. Otherwise, it won't work.
Okay, I think we have a couple of questions about which elements, but there is one. If you accept the phase, will the peaks from this phase be excluded from the next search?
No, currently it does not automatically exclude that. And that's actually the last example that I want to show you. I want to show you that despite that is not available yet, and it will be soon, that there's still a way that you can iterate the search when you have multi-phase situations.
All right,
But
then
it's going to take me a little bit of time to get through that because the example is a little bit more complicated. So I think it would be good. Maybe we continue with that and then we can go back into the questions afterwards.
Yeah. You go ahead.
So I will upload one more data set, and this is actually an iron supplement for treatment of anemia. So it has essentially the iron compound is the active ingredient, and then it also is mixed with filler or excipient materials that are part of the formulation that, kind of enhance shelf life, processability, and also make sure that you get the right dissolution profile when you actually take these supplements. So it's actually like an iron sulfate compound. So I know that to start. The wavelength already happens to be correct here because this is also a measurement from our system. So I'll just say, okay, generically, it's got to be something like this. Again, doesn't matter so much. And as initial start, I would just choose that it has to have iron in it and probably doesn't have 20 elements. So maybe let's guess like 5 or 6 or something like that. So could do find peaks. Another thing that is useful to know is that if you select many peaks, it's creating essentially like a registry signal from those peak positions and intensities and using that to search. So if you have many peaks in your search, it will slow down the propagation of the results. So if you kind of know, that there's a certain set of peaks that you're primarily looking at for a certain search, you may not need this many peaks in a lot of cases. So one thing you can do to actually speed it up is you can delete a bunch of the peaks. So I didn't show this in detail before. There's a second tab up here, which is the peaks tab. And you have all of the peaks that have been auto-generated here. And you can select all of them or a selection of them to remove. I'll show more you can do with that in a second. And just as a convenience, you see there's a little color marker after the intensity, and that actually just indicates which are more intense peaks. So light colors are very low peaks, darker colors are very intense peaks. You see that the red one here is the most intense, and that's because all of the patterns for this visualization are normalized to the maximum intensity. So the max intensity will always be at 1. So now, okay, I don't want to, select individual peaks through here. That's quite cumbersome. So what you can do is go to this interactive plot here, and I can just say like, okay, I probably don't need all of these high angle peaks. So I can zoom a box onto all of those. And if I do that, the peak positions shown will be updated here. So now I can select all of these and remove them and double click in the plot to zoom back out. And now I just have a fewer number of peaks from the high intensity Bragg reflections. So, okay, I'm gonna do my search with that. Has to have iron in it. And I get actually quite a large number of matches here, you see, because there's a lot of peaks. But if I look at the top rated candidate, I get actually what looks to be a very good match in terms of the peak position. There's a little bit of variation in the relative peak intensities, but I'm quite happy with that. I think that is pretty convincing. Oh no. Okay, sorry, my thing froze for a second there. I could explore this a bit more, so I can see like there's other candidates here. So there's also a monoclinic version of that structure, same formula, but slightly different. And I can see that there's some additional, well, I think there's some additional peaks for that one that show up. Oh, Oh no, my computer is slowing down. So, I mean, point being, I can go through and check other candidates to see if there's a better one. So I can accept this. Let's just start with the simple one. And now what I want to do is I want to check and see what am I missing. So actually, I'm going to zoom into the low angle region at low intensities, and I see there's a whole forest of other peaks in here that we didn't get yet. So I don't want to search on the stuff that I've already identified, as you've correctly asked, but I can't auto update there. So what can I do? What I can do is I can zoom out, select all the peaks, and just remove everything. So now I still have my confirmed phase telling me which peaks I've already identified, and then I can choose to select what else I want to search on. So the next thing that you can do that is a little bit more convenient is you can go into peak selection mode, which is this little arrow here. And I need to refresh this. My computer is lagging quite a bit. This is what I get for using Ubuntu. Sorry for that. Let's try this. Here we go. Okay, so now I can actually explicitly select peaks in here. So let's just choose a few of them. So this is literally like a point and click. So you go to the maxima of the peak that you want, click, and it will add a marker. If you don't like your selection, you can also click on it again and remove it. So this is fairly fast, hopefully, if you don't have too many peaks. And I'm not going to select everything because oftentimes, as I said, you don't need everything to get a positive match. So let's just get a few things here. And I'm going to use a little bit of knowledge of the sample because this often really helps to kind of further specify what you're looking for. And so in this case, I expect that this iron supplement is formulated with some sugars as an excipient. That's very common. So I'm actually just going to go ahead and specify the search into that space. So carbon, oxygen, hydrogen, 3 elements. And now I'm going to go ahead and search on the new peaks that I selected. Now I get a very short list. And again, top candidate looks to match quite well with a selection of these peaks. Could be that it's a second one here, also the same structure. And the fourth one is also the same. So we can already see this is sucrose. So it matches a bit my hypothesis there. Of course, I know the answer, but just to kind of demonstrate the point. So I can accept this phase now. And now I can reiterate this again. So again, remove all peaks. I should make sure I'm zoomed out. Yeah. Okay, let's zoom in again. Oh. And then we can do this selection again. So what am I missing? This guy, maybe that one, here. Okay, so I can run it again. Don't get anything that looks very good in this case. Nope. So maybe you need to include a bit more. So sometimes you have to play a bit around with which selections you're making. So we can try again. And again, I know the answer, so I'm cheating a bit. But actually, down here, you get the rest of the peaks, and this is actually lactose monohydrate. So this sample is made with two different sugar fillers, sucrose and lactose. And now I haven't gotten everything in here yet. This is where you can keep iterating this process. So just to sort of, well, I think I'll demonstrate it quickly. If I delete the peaks, maybe I want to kind of figure out what is this really low angle peaks down here. Maybe it's probably not a sugar in that case because the unit cells are generally smaller. So I might want to release some of the filter constraints here. Again, probably it's not stuff like that. Can search. So I get a few cases here. It's actually not these phases. There is one candidate that it gets from the COD that is interesting, which is this one here. Looks like a decent match for those first three peaks. And it's, I tell you right now, it's not the right thing, but it does have this long aliphatic carbon chains as spacers. And a common lubricant in these formulations is like sodium lauryl sulfate and things like that also have a similar structure. So this doesn't give you the right phase. And I think that phase is unfortunately not in COD, but it at least gives you a way to test, you know, are there some structures that might describe that and what are the properties? So of course you could guess from the angles that the unit cell has to be quite big for this contribution. But maybe this helps you kind of get some further ideas. So this is a way that you can iterate this process as is to do multi-phase search match, even though, as I said, the current beta version of this tool is not specifically designed for the multi-phase workflow. But that's basically what we're planning on working on next. So I think that's, I went a little bit longer than I wanted to, but I hope that answering some of the questions was helpful. So I would then kind of go back and let Sebastian discuss a little bit more about the process for those of you like who want to actually collect some data to work with on this. Maybe you don't have your own instrument or you want to see how the data quality can help improve it. And then I think we can go back into answering the rest of your questions.
Yeah, we have 19 questions already, so we'll stay a little longer so everybody can stick around. Yeah, so how can you get XRPD and total scattering PDF data if you don't have access to a synchrotron right away? We measure roughly every second week at the ESRF. We do perform the analysis for you if you're from industry. Happy to give you a quote for that. We also have a wide network to connect you with collaborators. And Maxwell has an open office hour to discuss, you know, kind of like how to send samples, how to analysis data, and what to do with your data. So you can go to our website right now. We measure the first 5 samples for free. And then you can actually use search match as well. So there were a bunch of questions if the search match was actually for free. Yes, this is for free. So you just register, you upload your data, you can use it. You can provide us feedback. That would be very helpful, actually. And while you do that, you also, you know, kind of like we're happy to measure the first 5 samples for free. And afterwards, it's not that expensive. So for academics, our prices start at 110 euros and go down rapidly. And yeah, we have users from the US, and it is not hard to center samples. So yeah, you can just go here. You can book a call with me and Max to actually discuss your concrete project. If you have any questions about that, please pick a slot for next week, and happy to do that. Week after I'm traveling, so then it's a little harder, but still happy to have the call. If we send our samples, then how much time it will take to be done? Yes, every 2 weeks. So we have our next beam time, I think, first week of March. Is that right?
Yeah, I believe it's March 3rd is the next beam time.
So yeah, if you, Mohammed, if you can send us stuff next week, you will have your data by the end of that week. No pressure. So
I mean,
yeah,
to take the pressure off, there's also beam time in the middle of March and the end of March as well. Although we are very happy when you guys make an account and send samples quickly. That's always very good.
So if you have not understood or worked with a synchrotron, the data is much better because we have that fantastic resolution that comes with working at the ESRF. We have a streamlined process, so we are actually measuring background and standards with it, and you have the data for that, and we provide. No, operando is not possible. Sorry, Mohammed. And you have the access to this for paid and for those first 5 free measurements. So yeah, this is our team. We are growing quickly. We're now 10 full-time employees, so working across Germany and France and even Italy. So yeah, go ahead, book a call, send samples, get results, and try the tool. Yeah, first one already did. Brilliant. Thanks a lot. And yeah, now I would go into questions. So let's go back up. Give me 1 second. I'm just going to filter this. Only questions. So this is now. Okay, so Daniel asks, really at the beginning, crystallite size 1 to 5 microns seemed a bit large compared to usual coherent domain size, which usually defines crystallites.
Yeah, for sure. I mean, probably if you have a 1 to 5 micron crystallite, there's certainly still probably some misorientations within that grain boundaries, anything else. So I agree that the coherent scattering length is probably still smaller than that. And actually that's why it works. If you had 1 to 5 micron perfect crystals, probably you would still not get very good data from powder diffraction.
All right, so then Mikael is interested in bimetallic nanoparticles of size below 5 nanometers. Some people publish these kind of supported nanoparticles claiming them as alloys. Do we have enough resolution to distinguish bimetallic alloys from mixture or intergrowth of such small domains?
So generally, that is not really a application that you could address from Bragg diffraction analysis. We do also do total scattering and PDF analysis, which is collecting the data over a much larger Q range to access a higher spatial resolution of the information. And then you can analyze the paired distribution function to look directly at the local structure. So I can't speak to if in your specific case it's possible to resolve the differences between those scenarios, but that would be the best way to probe that.
Okay.
We gave a talk about that, about analyzing nano catalyst materials and particularly some metal alloys and metal oxide nanoparticles a few weeks back, and that video is actually also available online on our YouTube channel.
Yeah. You can reach out to me to get the link. How would you recommend preparing powder samples from bulk metallic alloys to get good data?
Depends on the particular scenario. So I will be the first to say I have very little experience, little to no experience in processing metal alloys. So I think all I can really say is thinking about the principles of what you're trying to do, and really, working to validate whether you are doing it properly and getting the right results. So, try to obtain sensible crystallite sizes, or as was correctly said, coherent domain sizes that are actually suitable for powder diffraction. Minimize any undesired effects to your sample. So you You, in doing that, don't want to generate new phases, phase transformations, or the generation of impurities, reactions. You don't want to induce lots of additional defects into your crystal structure, which could increase the microstrain. So you need to be considerate of those things. And the best way to do that will depend on your specific material. So even within alloys might be that in some cases, you need to do something very different than in another case. So I can't necessarily be more specific than that, I think, without more details.
Can we analyze organic samples from this tool? Mutu Kumari was asking.
Yeah, so in the last example, I showed you the identification of two different sugar compounds in the material. So no, there's no restrictions there. It really just comes down to, again, currently, whether the materials that you're searching for are in the COD or not. But I can show lots of other examples of, we have lots of pharmaceutical data where you can, aspirin and citric acid and things like that you can find the phases for quite easily. So yes, it also works for organics.
In future versions of the tool, do you anticipate adding the option to do refinement after search match?
Possibly. It could be that we make another tool you can connect the results from this to. But yeah, let's say in terms of our platform, yes, we are thinking quite a lot about how to get you guys to quantitative results faster. So yes.
Can we identify different hydrates?
Again, depends on the case. So if you have completely different crystal structures forming depending on the hydration level, and those crystal structures are both in the COD, then absolutely. You can also have cases where you have sort of pseudo hydrate formation where you don't have like really crystal water, and it's really more like existing in micropores or interstitial spaces or interstratifying layers or something like that. So then in that case, for instance, in clays, more hydration will give you a larger interlayer spacing. So then you might be able to identify the approximate hydration level from that if it's known. But there might be cases where you have a range of water content that is not producing distinctly different structures and is maybe only affecting the lattice parameters. So definitely in the cases of different hydrate polymorphs or different hydrate structures, yes.
I think you have to answer in shorter because there's still more questions coming in than we answer. So I think this is just a comment. A helpful feature for search match exclusion would be a structure type in addition to composition, so that users can remove candidates that have been ruled out through indexing and/or whole pattern fitting.
Yeah, absolutely. No, it's a great idea. We have lots of ideas for things to incorporate in here, and so that we could release something to you guys, we had to choose which ones to include for the beginning. But we absolutely plan to add more filtering capabilities and more search functionality in the near future.
All right. For your synchrotron samples analysis service, do you have customers from the US? Is it easy to ship your samples from the US? Can you work with air-sensitive materials? So the first two questions I can answer, yes and yes. It is easy to ship from the US, and we have plenty of users from the US. Just follow the process, and you will get a performer invoice to lay into this package, and then customs is usually happy. And can you work with air-sensitive materials? Maybe in a one-sentence answer, Max.
Yes.
Well, even one more.
I'll give a little bit more. Yeah. So we also for air-sensitive materials, typically sent in coffee bags or under some other sealed containers under inert gas or vacuum. We do use a glove box for handling and preparing the samples. We typically basically fortify the sample holders to decrease the amount of diffusion of moisture from the air. And that's usually stable within the time frame of the measurements. In some cases, we add some glue or extra tape or gaskets that also further seal it. In terms of like highly oxidation sensitive samples, this is maybe a bit different in some cases. So I would say we're working quite well for moisture sensitive materials. But if you have like something pyrophoric that's going to light on fire if it comes into contact with oxygen, please don't send us those right now.
All right. I see lots of people are registering. Very good. Very good. For sulfides, seems like a full profile search match would be recommended. I think that's more rhetorical.
Yeah, I mean, I can tell you that, you know, I talked in the very beginning about like the trajectory of once you have candidates, you need to actually verify that your candidates are correct. And I always use this method. So I have sub-libraries of candidates that have been sourced in the search step. And then I'm generally doing a whole profile optimization of the candidate library to see if actually these combinations work together to actually fit the pattern. So yeah, 100%. You should be doing that.
So I think the next question is actually for Lucas, and I want to give Lucas a chance to actually say something so that everybody sees that he's really alive and not an AI generated bot that we put here. Can we upload the raw image data directly, or do we need to convert it to graph before uploading it?
You need to integrate your detector image to a 1D pattern to be able to use it at the moment. Yes.
But you said when we were off air that we are working on different formats to be uploaded, right?
Yeah, you can definitely. That's the thing that's not available to you yet, but to Max it is. So it's behind the flag. You'll be able to throw in your vendor formats like famous broker raws, analytical formats, which come straight from the machine into our tool without converting them beforehand.
Yeah, yeah, exactly. Just to add on to that, the issue is that in order to get from 2D to 1D, you need a lot of other files and information to do the process. So we don't have a tool set up to do all of that for you for any generic case. But as we're here to support you guys, if you have data that you want to process to 1D, you can email me. I can give you tips on how to do that, what software to use, or you can just send us your samples and we do all of the processing for you.
Brilliant. Is there a way to include peaks that were not added automatically? Yeah, well, you know, if I think you showed, you know, kind of like that, you can just click on the image. I hope, Fanny, that was answered. The question might have been on the geometry used of the measurements. Using only 2 theta MAS does not give the same intensity as theta 2 theta, then the score will be modified. So
yeah, so as I mentioned, the current iteration of the tool is actually optimized for measurements that we did. So for sure, if you have a very different geometry or you have significant different effects from, you know, your choice of monochromator on your system, you get different polarization correction and stuff like that. That can certainly have an effect on whether you'll be successful with data from your instrument. So we have tested quite a lot of data from different sources, different synchrotron beamlines, also different lab sources, and gotten positive results in many of those cases. So that's why we still provide that option. But yeah, this is something that we'll have to provide some functionality in the future to account for those kind of systematic instrumental driven changes. But I mean, if again, being candid, you should send your samples to us and then we provide the data that's optimized for the tool for you.
all right, then we have I think 2 questions about the video. So yes, I will share the video of this recording right afterwards, and so you can actually look up how to do things, and we may decide to actually cut the session and provide, you know, kind of like shorter snippets. But right now, you would have the opportunity to just look at the session recording. In the parameter vertical, please choose from file instead from sample. I am not entirely sure what this means. In the parameter vertical.
Yeah, the user is asking if we can throw in, like if we can upload files and not just use files from our system. So I think Maxi showed it, right? You upload data into the search mesh tool. So I think that counts as answered. So yeah, you can use external data for the tool.
Yeah.
How is it different from expert high score XRD data analysis?
I mean, there's various things that are obviously like very analogous in what you're doing because the process is quite similar. To be honest, I don't know the specific features of high score, so I'm sure that the search algorithm that it uses is probably a bit different, and I'm sure that there are different features available in there. So I mean, this is the first version of our tool. If there's things in high score that you really like, that you think this tool should have, let us know. Maybe I can speak to like what we look at as being the fundamental differences. Currently, this tool is free and the tool is available online. So you don't need to install or download or do anything that's system dependent. So you can make an account and use it. That's the difference between our tool and high score, kind of in crude basic perspective.
Okay. How does it handle background? We don't need to work on background as far as I can see.
Yeah, so that's actually a really good point. So there's two components to that. So on the one hand, there's obviously your experimental background. We remove that from all of the data that we measure. We measure it and subtract it. If you have data from your source, if you want to do that, you would need to do that beforehand. Of course, there's the other component, which is diffuse scattering from your sample. In that case, yes. So if you have a combination of diffuse scattering from a amorphous or nanocrystalline phase combined with sharp Bragg reflections from a crystalline phase, the diffuse scattering can modulate the relative intensities of your crystalline peaks. So if you only care about the crystalline phase, best practice is often to remove the diffuse part so you get back the best relative intensities. Currently, we do not provide the option to fit and remove the baseline like that. In many cases, we found that actually our algorithm still works pretty well, even if there is significant diffuse scattering. But if you have a case that you find that it's not working well, then you would need to remove the baseline before loading the data into the program. So I can recommend, for instance, that's very easy to do with a short Python script. If you're savvy with some, basic scripting, you could probably just ask ChatGPT for a script to do it, and I'm sure it will be successful. And then, I mean, there's lots of other sort of data handling softwares where you could do that. Just looking forward, yes, that is also a feature that we will introduce into our tool in the near future.
Brilliant. What if my sample are solid in a rod form of around 1.5 millimeters to 2 millimeters? Can this easily be measured with your facility? Well, I think the question is it thickness or kind of like?
Well, we can just tell what we can do. So this is what our sample holders look like. And sorry, there's like a bit of paper back here, but you see there's these little holes. That's the well where the powder goes. The diameter is 2.5 millimeters, and the thickness, not of the plastic part, but of the actual window, is 1 millimeter. So if your sample is 1.5 to 2 millimeters thick, it's a little bit thicker than the sample holder, but that's okay. We can actually section out the holes and put your kind of film into the sample position. But then the lateral dimension should be less than 1 centimeter by 1 centimeter. And then the thickness ideally is still around 1 millimeter. but we can go up to maybe 2 or 3 millimeters thickness, I think, and it shouldn't be a problem. So, I mean, unless it's like pure lead, which probably isn't good, but most, lower Z and even kind of like mid-range transition metals, we're working at 75 keV, so our X-rays essentially just punch through everything.
Yeah, no, absolutely. Okay. Are there any limits on this, on its use with external data? Can I advise the students who use my lab to use it? I think yes, right? I don't.
Yeah, I mean, if there
have
are
to.
limits beyond what we've already discussed, we maybe don't even know what they are yet. So feel free to explore and find those limits. But yeah, I mean, any data measured on lab sources, if you have the correct energy, you can upload it and use it. There may be other corrections that you need to think about making before using lab data, depending on the source. So in many cases, you have, for instance, issues with axial divergence. So you get like really asymmetric peak profiles. And you may also have cases where the Z error in the measurement because of the detector zero or sample displacement is systematically shifting your diffraction pattern. So those types of things may need to be corrected before uploading the data if you want to have accurate peak positions. And accurate peak positions are necessary to get the best possible result.
Yeah, but those students can also send in samples over to us and get them measured. So
yeah.
Are there any necessary pre-preparations for the samples before we send them?
You will get all instructions when you make the request. I mean, just to give like a basic overview, we typically ask for 30 to 50 milligrams of powder. As I kind of started with, like, you should process the powder to best sample form beforehand. So if the sample is single crystals, you should grind it into the right form. It's not really possible or feasible for us to know the best way to process every kind of chemistry and every kind of sample. So the people making the samples should do that to make sure that they don't degrade it. We, as I said, we can also work with like solids. So best case scenario, you have solid chunks of material that can also fit into those wells. But if you have sort of not thin films, please don't send us thin films. But if you have something that's like, some tens of microns or hundreds of microns thick, then, as I said, like if you have sort of 1 by 1 centimeter or less squares with sort of, 50 microns to 3 millimeter thickness, this is something that we can generally also measure.
I wanted to say, right, definition of thin film, right? You have like monolayers, yes, no chance, right? But 100 micrometers.
Well, 100 microns is not a thin film. If we go by the definition that the thinness means that the properties of the material change.
Well, I heard you. I have come to expect the unexpected, so I always ask, what is a thin film to you? So, so no, we don't do in situ high temperature study, and our max temperature is, what is the temperature at the ESRF lab? 23 degrees.
Room temperature.
Really, room temperature. Can you expand on the type of files an external user can upload? Maybe that is for Lucas.
I maybe Lucas, you can speak to that.
I mean, the feature isn't complete yet, so if you have a wish, let us know. I can tell for sure now everything that ends in XYE, so CSV files, comma list, tab separated files, so white space separation between columns. But if it's plain text, mostly column based, and then everything that's vendor specific is in the works. So I can't tell you really what's going to be there. So I know, right, Broker UML, Broker Raw, Panetical, name a few. So I'm mostly going to be there.
Right now, would it be fair to say that as long as it's multi-column format, that it's pretty insensitive to metadata headers or delimiters, or is there some limitations there?
I think that's limitations. So
Okay.
one row of header is probably allowed.
I think it accepts more because I gave it some stuff that had quite big metadata blocks.
Great.
But yeah, maybe, so if you get issues, then maybe check like if your columns are spaced by tabs or commas, might be something to check. And then I think it's also extension agnostic, right? Like as long as the format is right.
Yeah, I think so.
I uploaded text and Chi and
Awesome.
XYE, and I haven't had any issues yet. So, but yeah, please, you guys test it out and let us know when you run into something that doesn't work properly.
Brilliant. Regarding sample preparation, when can the milling procedure be considered sufficient for multi-phase materials? Again, Portland cement mortar, so that the sample can be regarded as homogeneous.
Yeah, I mean, that's something that there's, there's not like a generic a priori answer that always is going to work. You need to validate your preparation method for your particular materials. Of course, there are sort of like standard protocols for classes of materials that are a good place to start. So for instance, with samples like that, you might target like a Macron milling approach, which is a gentle milling. Time spans often go anywhere from like 10 minutes to an hour. And you typically add a little bit of solvent to lubricate the sort of rollers in the mill. And you want to get it down, as I said, to this kind of like, 1 micron size regime. But depending on your particular sample and what other fillers or impurities or other stuff is in there, might be that milling method is not sufficient for a particular phase. So that has to be verified. And in that sense, you can double check the results of what you get from microscopy, which might not be statistically meaningful for everything. So ultimately, you may also need to do a diffraction measurement to see, do you get good powder scattering from all of the phases, or do you have some contributions that are making nice rings and others that are still spotty? Then you may need to iterate, figure out what the contributions that are still spotty are, and then adjust your preparation method to account for those. I mean, it also depends on your end goal. So, I mean, you have quite a bit of space to not have perfect data where you still can oftentimes solve what you want to solve. So if you want to do like super high accuracy, quantitative phase analysis where you need really high accuracy even for minority phases, yeah, then you really don't want any of your phases to be spotty. But if you're doing just phase ID semi-quantitative analysis and you have bigger margins for error, it might be sufficient even if it's not perfect. So you have to make that assessment based on what your criteria for results are.
All right, brilliant. The next one is more I think, a meta question. Is there any opportunity for research scholars from India to get offline hands-on training program in your place where we can learn experimentally how the analysis is performed, or any offline workshops about the same? So generally, measurement, no. But analysis, we did an offline workshop in Bari last year. There's none planned right now, but I wouldn't exclude that. And we will, yeah. Oh, yeah.
Not that we are organizing it, but
Yeah.
I'm teaching at it, and so is Bernd, our other co-founder. There is the European Powder Diffraction Conference in Switzerland in June. And at that meeting, there will be a Topaz workshop, which will be a training workshop for using the Topaz software to do both diffraction and pair distribution function analysis. So that could be an opportunity, although of course, then it's could be a big travel.
Yeah, no, but you're right. At that meeting, there's an opportunity to get more hands-on training. If there is no match for the peaks via search and match, can I still display the calculated peak positions of the chemical crystallography database that I know is actually contained? Can I put in simulated data myself?
This is we had the question earlier about like being able to input your own references, and so I give the same answer. We can do this, and it exists in our sort of back end version of the tool, but we didn't release the feature yet. So yes, and it will be available in the near future, but it's not currently available.
Okay. Okay, so I don't know what that is. I want to do LFP, FP quantification on electrodes. I'm using transmission geometry and a molybdenum X-ray source. Do you think the microabsorption is still a problem? Or which other problem could interfere in the quantification?
I mean, off the top of my head, I don't know. What I recommend, there's a really nice little widget from the APS where you can calculate the absorption for a given sample chemistry and size and X-ray energy. So that's a good, easy first place to start. I don't know the URL for it, but if you just go into Google and type in APS absorption calculator, I'm sure you will find it. So I would start with that, and then you can see like whether you're in the right range or not. So I mean, in general, you want to be obviously away from absorption edges so that you avoid significant absorption and significant fluorescence. And then in terms of transmission, you typically want to be in the sort of like 30 to 50% range, because also, especially for lab sources, if the transmission is too high, it means that your scattering statistics will not be as good. So you might need to measure for longer. I assume in this case, probably you get pretty good scattering statistics, but yeah, that would be a place to check.
Okay. Then I think we had a couple more questions. Going back to the sample preparation, are there any sieves you recommend with micron-sized meshes, ideally without a large diameter, for dealing with smaller volumes of sample? Sorry, actually, that's a very good question.
That is a good question, and I have to say, no, I don't. I'm sorry. I'm sure there's probably other people in this call who I can see some names who I bet know more about that than I do. My background is mainly in looking at like nanoparticles and stuff that you just never really care about sieving anything or really worrying about like, you know, kind of preferred orientation or large particles. So no, I'm sorry, I don't know.
And then Knut is asking, how should we reference to the tool? Do you plan to have a publication or some document one could name in manuscripts?
That is a really good point, and I have to say, I don't think we explicitly discussed it. But yeah, Lucas, we should add a maybe slightly different acknowledgement statement to the tool, because then it's not related to some of the things in the other one. So thank you for thank you for bringing that up, Knut. I think that we'll add a statement into the website for that. But I mean, in general, for anybody, if you're, you know, kind of publishing some results from some aspect of our platform, if you are unsure, then just reach out to us and ask.
Yeah. And then last question, have you participated in the Reynolds Cup competition for quantitative analysis?
Yeah, we participated last year, and I'm planning on participating again this year. So should be fun.
Yeah. And then the last one is, what is the material of the sample holder? But the sample holder is actually not transmitted through. So I think it's more a question of the windows.
Yeah. So, I mean, just to give a complete answer, the sample holder is, I believe, polymethyl methacrylate. But yeah, it's your beam's not going through it. So, I mean, if you're trying to put some solvents in there, yeah, it could be a question as to whether you can dissolve the sample holder or not. We actually did recently have a case like that, and we had to load the samples in a slightly different way, which is also possible. The windows are made of Kapton, which is generally much more robust against all different kinds of solvents. And actually, yeah, that's what we use to work with things that dissolve the sample holders, kind of internal Kapton vessels.
Brilliant. So there is still 60 people in the call. I do have to say thank you very much. Please, book calls with us. Get to our website, log in. We're happy to measure your samples. Happy to support your research in the future. And see you in probably 3 weeks, or if you book a call, much earlier.
Thanks, everybody.
I'm just waiting for everybody to
I'm still waiting for like another couple of questions to pop in there. Wait a second.
No, but it's so nice, to see. All right, so let's end this. Thanks.